It is my pleasure to introduce Professor Ankur Mehta. He is an assistant professor of electrical and computer engineering at UCLA and directs the Laboratory for Embedded Machines and Ubiquitous Robots, LEMUR. Pushing towards his vision of a future filled with robots, his research involves printable robotics, rapid design and fabrication, control systems, and multi-agent networks. He has received the NSF Career Award and the Samueli Fellowship, and has received Best Paper Awards at the IEEE Robotics and Automation magazine and the International Conference on Intelligent Robots and Systems, IROS. Prior to joining UCLA, Professor Mehta was a postdoc at MIT's CSAIL, investigating design automation for printable robots, and before that, he conducted research as a graduate student at Berkeley in wireless sensor networks and systems, small autonomous aerial robots, rockets, control systems, and MEMS. While not in the lab, Ankur enjoys puzzles, ultimate frisbee, board games, and social dancing. Ankur, take it away.
Great. Thank you for the introduction, Jeff. Thanks all for showing up here. Before I get into this talk, I'll say this, my talk is a little bit perhaps different than those you may have been experiencing before. I have certainly some amount of technical content, but a lot of the first part of this talk is going to be less technical and more sort of motivational and social sciencey, I guess. So I welcome conversation here, and I think that's a large part of what I'm trying to do with these talks is to inspire some conversations. And so before I get into that, I want to start at a very high level by talking about my overall research group and the vision that we here at the Laboratory for Embedded Machines and Ubiquitous Robots try to accomplish. And that's this idea of a future where robots are everywhere. And so there's a lot of technology that needs to go into accomplishing that. And we look at this from the full stack, in terms of control algorithms and sensing, perception, autonomy, and manufacturing and materials. And ultimately, the goal of this is to build this future where not only are robots everywhere, but robots are accessible by everyone. And that's really what I'm going to be focusing on today. And in fact, that last bullet point here, this idea of using computational tools to create robots by everyone. Now, there is all the other work. And so if you are interested in questions of planning, control, perception, user interfacing, and so on, feel free to go to our website. There's a lot of information there. Reach out to me, send me an email, and I'm happy to go over this in more detail. But really today, we're going to focus on this on the question of accessibility and the ability to create robots in a more general way. Now, I'll say that I'm just the pretty face talking to you guys here today, but fundamentally all this work is done by my group, a bunch of amazing graduate students and undergrads, made possible through sponsorship through a bunch of different agencies. Ultimately, this all relates to you guys. If we can get more of y'all involved in this, we can do more here. And so with that, then I'll go ahead and really focus on the work that we're doing. But like I said, I'm going to start with the motivation, with this question of why is this the target of LEMUR? Why is it that our focus is on accessibility? And I'll motivate this with a bunch of statistics that I've gotten from a variety of sources. But I do want to preface this by saying I'm not an economist. I'm not a social scientist. I'm just an engineer that looks at data and makes my own personal opinions. So I'll present the data and explain what I think about this, but I really do encourage you all to take a look at this data and draw your own conclusions and figure out what this means for you. I'll present a bunch of correlations, which clearly are not conclusions, but I will use that to drive where we're going with this. And I'll start with the metric of income inequality, which is, which has been a hot topic in recent months, recent years, but it has not been, just because it hasn't been as publicly talked about doesn't mean it hasn't been an actual concern. There's a large gap between the incomes, the earnings of the upper portion of the population and the lower portion of the population. That gap between incomes has been increasing over the years, and if we integrate this over time, that relates into a wealth inequality, where those who have continue to have more, and those who don't have end up having less. And we can take a look at those who don't have. In fact, the bottom 50%, the bottom half of the population, ends up currently having a far smaller portion of things. Wealth in this sort of capitalistic environment that we live in is a metric for access to a whole range of things. And the thing that I'm going to focus on in particular, what this translates to is access to technology. And we can see that there's a large gap between your income, your wealth, and what kind of technology you can access. Many of us, almost of those of us in the audience here, and I'll say myself included, take things like a laptop or computers in general or internet connectivity for granted. But that is not a thing that is universally taken for granted. These are just in the United States. These numbers come from the United States, and you can see that for a segment of the population, a lot of this technology is just not there. And the US is one small segment of the entire world. And so there's this gap between what kind of technology is accessible to large parts of the population. And this is a problem, not just for the sake of the technology itself, but the technology translates to education. And in this, in the past 2 years, we've been under this pandemic where technology has been a core driver for remote education, for sort of how to access education in the pandemic. But we can sort of use this as a metric. It's the data that we can then translate to a broader sense. Now, there's a bunch of data presented here, and it's broken up into several different axes. I encourage you to look at the various different forms of correlation. There's correlation across race, correlation across access to technology, and correlation across educational outcomes. And ultimately, this is all painting a rather dire picture, which is that the income inequality translates to wealth inequality, translates to technology inequality, translates to educational inequality. And this is a problem. We can say that it's not just an educational problem through that pipeline. Here is sort of the very specific resolution of that, which is, rather than going through all those steps, income translates to education, which goes on to more access to stuff. In this case, a metric is the GDP, which is a measure of wealth, a measure of how much production capability exists. And sure, everything took a hit when the world shut down for 2 years, when especially schools shut down for 2 years. And that hit is certainly tied to the impact of education on future productivity. But it still comes back from income and the income inequality. When the income goes down, the future capabilities, the future production similarly goes down. And we can see another metric that captures that by taking a look at educational destinations, where like the end of the educational pipeline, again, as it relates to income, as it relates to wealth, and as it relates to sort of this entire chain of consequences. And for those who don't have, they end up having less education. And for those who do have, end up having more education. What this means is we end up with this feedback loop. And this feedback loop is, it's a positive feedback loop in that less access to technology means less educational capabilities, which means less economic potential. And that lower economic potential leads to further reduced access to technology. Now, I say positive feedback loop in the engineering sense. This is a negative consequence, but positive feedback loop, as as engineers, we know that positive feedback leads to the system railing out at the two extremes. And that's not something that we want. We want to try to improve capabilities. We want to try to improve outcomes for all of humanity, not just a very small subset of those who have. This growing feedback cycle is unsustainable. Now, I'll say that before I get into perhaps the silver lining, this does get just a little bit more dire. And it's this question of, we have this particular feedback loop, And if we take a look at the central element here, this question of education, it's not just a positive feedback loop through this cycle, but there's another question of even even whatever education you do have access to, there's a question of motivation, engagement, the fact that that communities that have lower income prospects, that are in a more economically depressed state, impose a lower motivation for education on their community, and this shows up in truancy. And this there's been this is a study that was done in LA and California specifically, but it's sort of a more general trend that those who have reduced access to education, those who have reduced income potential, also have reduced motivation for continuing through the educational process. And it starts early, in that the lack of attendance at school translating to a lack of engagement in the educational process starts as early as kindergarten. And of course, this further compounds that feedback cycle that I've sort of internalized as a core driver behind a lot of the problems that the society is facing today. And so with all of that doom and gloom, I'd like to now turn it around and talk about how we can approach this and what we can do to hopefully make the world a better place. And that stems from this concept called the endowment effect. And it's this idea that creation, making, the ability to be directly tied to the ability to create something, to be able to create anything, no matter what it is that you create, the act of creation itself adds value. It brings value to those creators. And that is a thing that we can now use to drive up motivation, to increase access to education, and to break this cycle. Now, that analysis was done for makerspaces. Makerspaces are one instance of this. I want to bring this in a more broad sense. I want to be able to take this and say, how do we take everything that we have been a part of, we as in engineers who have gone through the educational process, in terms of giving us the ability to create technology and participate in the technology creation conversation. How do we take that ability and bring it to a broader population? Those who have not yet been a part of this conversation, those who lack the access to the resources to make this happen. If we can do that, we can break this cycle, and we can then go ahead and improve outcomes for sort of a broader range, in fact, overall, all of society. Now, I'll take a slight detour and say, this has been my motivation for a lot of the work that we do, is trying to improve equity, trying to improve accessibility for more people, to broaden the scope. But if that's not your thing, there's still value to the work that we do. And for that, I'll take a step towards the abstract a little bit. This is a figure from one of my colleagues who was looking at the question of fairness, equity, sort of these fuzzy goals in medical devices, but it's a more general framework. Across engineering, we have trade-offs. There's always going to be some trade-off when there's a constrained resource, and we can look at a trade-off as this Pareto front. And in this case, we can take a look at some Pareto trade-off between questions of accessibility, of access, of equity and fairness on the vertical axis here, and questions of performance, questions of sort of the metrics that typically show up in engineering research. Things could be, like for robotics, could be speed or strength. It could be, for machine learning, it could be accuracy or latency, whatever it may be, whatever the engineering capabilities are. We can call that the other performance, the other metric that we're trying to evaluate against. And at some point, we can say maybe we're currently at 0.1, and that lies on some Pareto front. And if we focus our efforts on improving fairness, on improving accessibility, on improving any particular characteristic, in this case, we move out to 0.2, even if we don't necessarily improve the canonical engineering metrics, we have pushed out that Pareto front. And as a result, when we push out that Pareto front, we have increased capabilities, and we can use that to improve sort of the standard engineering metrics. And so bringing that to sort of a very a more specific approach, I want to take a look at this, the philosophy of Unix. I'm a Linux user. I use sort of free and open source tools as much as I can. This philosophy starts with this one bullet point, which is have each technological solution solve exactly one problem. And you see this in Unix utilities, very small, very single functional utilities. We can take this into the robotics world and see what is the current state of robotics. How are we working towards robotics engineering and as a sort of proxy for technology itself? I'll show some videos from the DARPA Robotics Challenge. This was a video that was run. This was a competition that was run a few years ago to try to get robots to participate in a sort of an obstacle course reminiscent of something that a human may try to do. And these are all a whole bunch of very cherry-picked examples, but you can see these robots failing quite dramatically. And of course, like I said, these are cherry-picked examples. There were certainly plenty of examples of robots doing very amazing, impressive things. But this is an example of a system that sort of runs counter to that Unix philosophy. These are systems that are trying to do a lot of things. And there's two consequences to that. One of which is, of course, these systems are very expensive. Each one of these robots costs on the order of $1 million. And of course, that is very inaccessible. There are very few people, very few researchers, very few individuals that have access to this technology to even begin to try to do any kind of research in this space. But there's another point as well. And that runs going back to this Unix philosophy, looking at this third bullet point, which is that in order to develop and to improve capabilities, there's this notion of trying and failing and iterating. Now, when you try and fail and you have to throw out something that doesn't work and work on something and build out something that does, when you go to these large, expensive platforms, you may feel very hesitant to try something that would break. You will certainly be very hesitant to throw it out altogether. And as a result, you take less chances. The act of creation is inhibited by the fear of failure when that failure translates to a large cost, that cost being the ability to do further research. And so this gets to this idea where being able to execute on the creation process with lower resource investment adds value, adds more performance capabilities in that same in the same breath as it adds accessibility. And so that's what drives our lab's research, that drives the work that we do here. It's this idea that we want to be able to give the ability to create to as many people with as low resources as possible. And in fact, that leads to the title of this talk, and the target that we have set for ourselves is to bring the cost of creation of robotics, take it all the way down to $1. And that's sort of an arbitrary, nice metric that gives us a nice clean number to address. But fundamentally, it's all about improving the accessibility for creation, improving the accessibility for participation in the technology conversation. And so that's the concept that motivates the work that we do in our group. But so this leads to sort of the core technology that we're working on in our group, and it's this idea of printable intelligence, printable autonomy. And it's this idea of taking robotics and making it out of accessible materials. In my mind, accessible materials translates to origami. Paper is something that is sort of, if not universal, at least ubiquitous. There's a lot of access to paper. The tooling, the infrastructure required to work with paper is very prevalent. And in fact, people start creating with paper before kindergarten, in pre-kindergarten, almost as early as you're able to interact with tools. And so we can say, we can draw some patterns on paper. This is a particular design that we have. We call it origami style engineering. It's not strictly origami because you cut it out and you fold it up. If you have access to more resources, you can cut this out with a laser cutter or with a paper cutter. But if you don't, you can cut it out with scissors or with a knife. You take it and then you start folding it up. As you fold this up, you introduce electronics, and you can end up with a robot. You can end up with, in this case, this is a design for a two-wheeled robot that can drive around and really not a whole lot else. But this is something that you can create, that can be created for very low cost. In this case, this particular robot costs on the order of $10. And this is one design, but we can extend this to other designs, and we can have four-wheeled robots, and we can have robots with steering capabilities through hinges and joints. All of these are made out of paper with a small set of off-the-shelf electronics. This gives us a low-cost platform. Now, we're not at the $1 range yet. Like I said, these robots cost on the order of $10, but this is a step towards improving the accessibility. Now, these robots, the goal is not to build a robot on which to where the robot itself is the end of the objective, that the robot does something that we want. The goal is to use this robot as a platform for driving technology creation. And so we can use this platform to think about various questions of automation. We can talk about obstacle detection, and we can include some low capability sensing. In this case, we're adding a 10-cent sensor onto the front of this, and we can say this is something that we can now get to the next level of autonomy, which is obstacle detection. We can do feedback control, and now we're going to add, maybe in this case it's about a $1 sensor, but it has some inertial sensing, and we can do some kind of feedback control. We can go up and even use this platform to do much more sophisticated analysis. In this case, we can use computer vision. And of course, as we start moving up in capabilities, we start moving up in cost as well. In this case, this particular camera costs on the order of $50, but we're working on bringing the cost of this down to on a $7 platform that we're working on. But you can do various forms of vision processing. Ultimately, and one more thing that you can do is with this, you can do multi-robot systems, where if each individual robot costs a low amount, you can build a lot of these, and you can talk about questions of networking and point-to-point networking, multi-robot networking, and so on. Ultimately, all of this is going towards this idea of using this origami-inspired process to take a very low-cost structural material, a very universal or at least ubiquitous material, along with its tooling and along with its infrastructure, to be able to create this low-cost platform. Now, everything that we've done here is focused on the body of the robotic system. This is sort of the mechanical structure that gives this its embodiment, but in order to give it its behavior, and we're turning this into printable paper. In order to give it its behavior, there's a lot of other components. There's sensing and actuation with the processing in between there to give it its programmed or controllable behavior. And for all the work that I showed earlier, this makes use of discrete electronic components that you can buy from various suppliers or hobbyist shops. When I say that this system costs between $10 and $50, the large chunk of that cost comes from these discrete components. There's also a question of the power supply. There is another big chunk of this that comes from the battery that's driving this. But what we're going to look at now as well is trying to take these discrete electronic components and make those printable. And once again, just a reminder, I'm using printable to mean accessible in terms of materials and infrastructure to create with this. And so, we've done a lot of work on making the bodies out of folded paper. What can we do about these electronic components that give it its functional behavior?
Professor, can I ask you a question?
Please do, yes.
I was wondering if you could talk a little bit about what kind of commercial things like this exist in terms of little hobby robots or like for kids or that sort of thing. And like, where do you see the barriers to that still be? Is that in cost? Is that in function? Just a little bit of context for us.
Great, thank you, Kim. Yeah, I think that's a great point that you bring up, is that I am absolutely nowhere close to the first person to think about accessibility in robotics. to think about what it takes to bring the cost down to widen the scope of people that can participate in this. And there's a number of hobbyist ones. I can't even go through all of them. But I think the largest difference here is that a lot of the cost is scaled down by economies of scale. That you can get robot kits where you can get this, where you can get nice aluminum bodies with microcontrollers and motors and so on. I think the lowest cost kit I've seen is, again, on the order of $15-ish. And it doesn't really necessarily have a clear name for it, because you can buy it from any number of suppliers that are sort of mimicking the same process. I don't know which one was the original one and which one are all the copycats or knockoffs or improvements, however you want to view it. So there's sort of that space of designs. There's and basically you get one robot, and it could be like very much like this two-wheeled robot. You get two wheels, you get a microcontroller. It has some interface where you can drive it around. Those are generally on the order of $10 to $15. There's a different space on sort of I guess other robot kits like the TurtleBot or other things where it's a little bit more expensive. Now we're talking in the $50 to $200 range, where you get a little bit more functionality, you get more programmability, you get more interaction capabilities. And I guess it's a bigger kit that you can use sort of for other things. And again, most of them are these sort of wheeled robots that drive around with various forms of sensing and interaction with the world. The large challenge to all of this space is that you get a single robot, and then your interaction with this robot comes from programming its behavior. What I'd like to focus on, when going back to sort of the earlier parts of my motivation, is the ability to create the robot itself. Now, creation does take many forms, and you can view programming as one element of creation. But in terms of the physical creation, in terms of the physical embodiment, you have less control over that in sort of these platforms. There is the other space which allows you to create the physical body, which allows you to sort of play around with any component of the entire robotic system: the body, the structure, the morphology, which includes what the sensors are, what the degrees of freedom are. I think sort of the biggest player in that space may be the Lego Mindstorms. And those, again, are on the order of $200 plus or minus. And so that's the gap I'm trying to hit. I want to get down to the cost of these individual robot platforms that currently get their capabilities through mass manufacturing, but not make it mass manufactured. Make it configurable, make it so that the participants, that the users of the system can create their own systems.
That's really helpful. Thank you.
And so, the bodies come from paper, or in this case, I say paper, I sort of mean flat sheet material. Paper is an example, but there's many things you can use. You can use polyester sheets, which are, again, similarly low cost, have different mechanical properties. We can use this to form the body. Now, if we want to extend the notion of printability, the accessible materials, we'll need something else for the behavioral parts. And so we'll throw on thread. Now this is nylon sewing thread that's coated with silver paint. It's, again, very low cost. It's not quite as ubiquitous. It's not quite as universal, but it's fairly accessible. And there are alternatives as well. Nylon sewing thread itself is pretty universal, and you can play around with it. But we're using this to make it a little bit easier. And with that, we can now incorporate the control, the sensing, the actuation into a fully printable robot. Now, I say we can. That has been the research that we've been working on. And so I'll jump right to the punchline of that and talk about this particular design that we've created that makes use of the mechanical body and this active electrical material to make a non-trivial sort of programmed capability. In this case, it's oscillation. So this is our oscillation that when you apply a constant power source to the device, it'll switch back and forth between two different states. Now, it does require external power, for which you'll need some kind of power supply. It could be a lab bench supply, it could be a battery. Again, power is not something that we've spent a lot of time working on, but of course it is something that is a component of this. And so we'd love to build more collaborations in this space. In this design, we end up using about 40 cents worth of material to build a, this is, you may not consider this a robot directly, but to build a, a sophisticated sense, plan, act system, electromechanical system with non-trivial behavior. And it takes 40 cents to build. It also requires some amount of engineering capability to build. This takes somebody who's sort of new to this process about 2 hours to manufacture. Once you have done a few of these, then you can get it down to an hour. So somewhere in between there, you can go ahead and build the system. Now, this is just a component of a larger, this is a component that can often, that you can sort of incorporate into bigger designs. But before that, here's sort of a view of how the system works. And as you apply constant current to it, the two conductive sewing threads, the nylon sewing thread actuators, will alternately pull the central element, the central beam, back and forth. And so we can take a look at that point and plot the motion of this point over time. This is sort of an example or sort of a characterization of how the system works. A lot of it this entire behavior is defined by the geometric structure. Going back to the core principle that we started with in terms of accessible materials, this is driven by the paper design itself. What the strings act as are thermal actuators. They when we start in a particular state, let's call this state 1, the actuator on the right is in tension, which means it makes electrical connection and therefore has current flowing through it, and it starts heating up. As it heats up, it contracts, and at some point it contracts enough to cause the beam in the center to snap through to the other state. Now, when it's in the other state, as it has flipped sides, the beam that had been pulling is now no longer under tension, no longer has current flowing through it, starts to cool off. Meanwhile, the other side has now been put in tension, it heats up, pulls back to the other side, and eventually it'll snap back to the original state. Now it has this periodic property, it can oscillate back and forth, and we get this oscillating behavior. This is a component that we can now use to make more sophisticated robots. This is, again, a benefit that comes from, we started with this notion of accessibility to make low-cost paper robots, but paper itself as a mechanical material has a lot of interesting properties, one of which is it has flexibility. We can use that flexibility to create joints, to create revolute joints. And that means we can translate the linear motion of this oscillation into rotary motion. That rotary motion can be used to flap a paddle. You can sort of look here that rotary joint. We could go ahead and design a very sophisticated mechanism, and plenty of mechanical engineers have gone through and created this mechanism. Or we can come up with a very simple one, which is just having a paper go through a slot. We can cut a hole in the bottom of it, stick a piece of paper down, add a piece of tape, and we're done. We've taken the sort of a lot of this work that maybe people have played around with as in origami processes or whatever you do when you play around with paper, and translated that into an engineered solution. When you do that, you end up with this origami swimmer. Now, what this happens, you still have the back and forth linear motion, but as the centerpiece of the oscillator oscillates back and forth, it translates into rotational motion of the paddle, which, when put on the surface of water, causes this thing to move forward. And so under applied current, we get the oscillation, which flaps this thing, and now we have what is now more visible as a robot. It's a robot that swims on the surface of water, and it is entirely made. This similarly costs 40 cents. It may be 41 cents because we added a little bit more paper to the bottom. Now, just as a point of note, I'm saying paper. I use paper to represent a broad range of flexible structural materials. In this case, it's polyester sheet. Same cost as paper, just doesn't get soggy and doesn't sink. So this is one way of taking that actuator, that oscillator, and turning it into a robot. We have another one where on both sides of this oscillator, we put a little mass. In this case, it's just a piece of foil that we wrapped around to give it a little bit more inertia. And then as this thing oscillates back and forth, it generates impulses. If we put little flexible legs, again, a benefit of the structural material that we used, if we put the flexible legs, we get asymmetric friction, and we're able to now build a robot that walks. And this is an example where in this case, this was sort of the first iteration. We put it on a string to keep it aligned. Instead, we could put two of these actuators on the left and on the right, and that'll give us the ability to steer. And now we can have things not going just in a straight line, but walking back and forth and moving around, all for the low cost of 50 cents. Now, this mechanism, it's not just about, so here's some data about it. You can see it walking forward. Not necessarily the most exciting thing. I think videos are more fun. But we don't necessarily need to use this just in the sense of building robots. Although I'm a roboticist, I love robots. I find them the most compelling. Other people may view things differently. We can take the same oscillator and say, instead of using this to generate electrical signals that go back into the actuation, we can also use it to drive electrical signals as an electrical oscillator. And we can have this oscillation motion get fed into LEDs, and we can make an LED display that's animated. And of course, this is something where we just did this as sort of a fun visual, but we now can sort of see how this particular mechanism can apply to a much broader range of creativity and a much broader range of creation. We can take this design and take it one step further. The designs that I showed earlier are oscillations. They're a single prescribed behavior. But we can generalize this and turn it into a logic gate. In this case, a multiplexer that is the basis for universal logic. And so the most simple connectivity turns us into an inverter, where we're using a switch to represent any kind of singular input, where it flips the output, it inverts it according to the switch. But of course, we can use this for more logical gates. We can have and, or, not, XOR. We can have all range of computation. And as a result, now we can start including intelligence along with actuation and sensing, intelligence and actuation and mobility into these robots. Sensing is another one, and that's going to be the work that we're working on going forward, is including this. Right now, the sensing is interaction with the human user, but it sort of can expand to feedback controlled robots and so on. Now, going back to this idea of the growth of the Pareto front, we drove a lot of this design and this engineering based on how do we bring the cost down. And all of these robots are very low cost. They're less, these specific robots are less than $1, not counting the cost of the power supply. But we did get some interesting sort of conventional robotic metrics improvements out of this. And one of which is this idea of performance under challenging environments. This has no electronics in it. It doesn't have any electronics because we didn't want to pay the $5 or $10 to put a motor and a microcontroller on this thing. But now without electronics, there's nothing to get short-circuited with water. Sure, there's electricity flowing through this. You probably don't want to have this running underwater while you're sitting in the water yourself. But ultimately, the system works just fine when completely submerged in water, not something that can be said of conventional robotics. Similarly, it works, again, just fine under incredibly strong magnetic fields. This is something where, again, any kind of conventional electronics won't work. If you wanted to put this in an MRI, if you wanted to do some kind of actuation, some kind of feedback inside medical equipment, you would have to go somewhere else. And this, even though it costs very low amount, is something that expands the performance envelope of robotics as a whole. And so that's the engineering that we've put into creating a whole bunch of new designs, a whole bunch of new devices for the generation of low-cost robotics. This may be a good time for another pause. Are there any other further questions about sort of the mechanisms and the sort of the structures that we've designed and created within this space of accessibility?
So we have a question from Mark, which is, could you comment on the longevity of these paper robots? Curious about the benefits of ultra cheap versus more expensive, but more durable.
Great, thanks, Mark. This is this is sort of a question. Let me back up to there we go, to one slide here. This is the oscillating walker. So it's just switching back and forth. In terms of longevity is absolutely one of the metrics that shows up a lot in conventional robots. And that's because you spend a lot of time and money and resources creating a robot. You want those resources to translate into the functionality of the robot for an extended period of time. In this case, you are spending resources on building the robot. In this case, it's the time to fold up the robot, an hour and a half. And here's just one longevity study where you can see this robot just continue to skitter along for 10 minutes. In this case, it's 5 minutes. But this is one thing. We took this off of the mobile platform and just had this oscillator running, and it was able to run for several days with no degradation with negligible degradation in performance. I think we got up to 10,000 oscillations or something like that, just because that's a milestone that is notable. After a few days, it did start to degrade, and that was at the center, because this is a thermal actuator. We started getting fatigue in the plastic material since we're using polyester. Had we been using paper instead, paper doesn't have the same thermal properties. We probably could have gotten more. We didn't really focus on that all that much, because fundamentally the point of this is to talk about creation. Going back, if you remember the Unix philosophy, bullet point 3, fail early, fail often. We want this to work for the duration of your experiment. And then the idea is that you haven't invested all that much resources into it. You make an iteration of the design. You come up with something better, something different, something new, and then you go ahead and use that. This design is far more about iteration, iterability, and new creation than it is about longevity. That being said, it does have we have done some longitudinal analysis that says it lasts for a good number of experiments before it starts to degrade. And so now, if there's no other question on that, I want to translate over into the next part of this, which is, we talk about the structure and how to manufacture it, but we also need to come up with ways of realizing the designs that we then want to manufacture. And I'll briefly run through sort of a framework that we have. I don't want this to be the focus of my talk, but if you have more questions, I'll be happy to get into it later. We have a framework, a design framework, a computational design framework that allows a casual user to input a very high-level specification, a high-level specification of the design, a high-level specification of the environment in which that design wants to operate. And we can go through and run some physics-based simulations to get some performance analysis. Going back to the initial robots that we described, we can sort of talk about how we can implement this in our analysis system for the wheeled paper robots, and we can simulate it in a physics-based environment. We can go ahead and manufacture it and run it in real life. We can try it on simple environments or perhaps more complex environments where we're trying to do this matching between the creation process and the operation process. Fundamentally, this comes down to the core point, which is that up until now, designing robotic systems, not just cut and fold robots, but in general robots as a whole, have been limited to those with experience. And so what I'm doing now is focusing on a different slice of the accessibility question. Up until now, going to this cut and fold robot meant reducing barriers to participation, improving accessibility by lowering monetary cost. But the question of design, which is half of creation in addition to manufacturing, is that you need to go ahead and have expertise in order to design it. And that comes because analysis of these integrated electromechanical systems, perhaps with additional subsystems involved, requires an engineering background. Either you have very high fidelity analysis tools, perhaps finite element or other numerical analysis tools, physics-based analysis, that you need to figure out how to use, because the learning how to use those tools requires experience and background. It also requires a lot of computational resources. Again, translates this for experts. You could try to find simple models and using basic kinematics, but kinematics, even though that requires a bit less engineering background, you now need more engineering background to understand where those assumptions and where those shortcuts fail to account for reality, and how how can you bridge this sort of this model-based reality to physics-based reality. And again, that needs expert analysis. That needs expert understanding. And so the question for accessibility on the side of design is now, how do we make it such that the same people who we have now given access to in terms of cost for manufacturing, how do we make that same demographic have access to the design process? And so for that, I want to go back to this oscillator and say, what we're trying to do in this case is build something that switches back and forth. The key parameter of this design is the oscillation period. That's this is sort of going to be a metric, a stand-in for a general design process. We have some vision that we want to realize, and we want to be able to implement this using our cut and fold manufacturing process. Now, how do we specify this oscillation period? We want to go ahead and we can take a look at this, model half of it as a single force applied to a bistable beam. And now I'm going to run through what we have done. This is the point at which in every talk you have a bunch of really fancy looking science, and everybody is lost anyway. So I'm just going to run through this and say what we do is we figure out a whole bunch of constituent mathematical expressions, take all of that math, couple it with actual physics understanding of mechanics and materials. We're going to go ahead and do some understanding of system models and how to translate sequences, how to translate signal sequences. And we're going to put all of that together, munge it up, and get our solution of how do we get the period, how do we get the oscillation period from the design. Great, everyone can now see this, and this is amazing, right? Well, maybe, not quite. The thing is, though, all of that analysis that we have done, that we went and put into the fancy science as engineers with the experience that we can go ahead and investigate this, we can now capture all of this within a mathematically defined constrained optimization problem. This is a problem that that we used our engineering abilities to create, but now we don't need any engineering abilities to solve, because we have optimization solvers that can go through this. This becomes a program that runs on a computer, and you can just go ahead and query this to come up with your design answers. And so for an example, we could say, let's say we wanted a period of, in this case, 4 seconds of our oscillation. We want our robot to take a step every 4 seconds or swim its paddle every 4 seconds. Give us a design for this. Well, what is the design? In this case, we're talking about a paper structure. It's the geometric parameters. How do you cut the string? How do you cut the paper? What are all these right things that you do that you then fold up to make the design you want? We get one more, we get another free parameter that we can change. Let's give it an optimization target as well. Not only do we want it to be 4 seconds long, the period to be 4 seconds, but if we're going to be cutting this thing out of paper, maybe we're cutting it with a knife and a cutting board, we're not necessarily going to be very precise about this. So we want this to be robust against imperfections in the design parameters itself. And we can throw this in a numerical optimizer, and we can get a result that as we make our design less reliable in terms of the manufacturing, we still stay within 10% of the desired period. Whereas, of course, if we had done this naively, if we just picked a random point, even if we got the right target period, which is not guaranteed to begin with, but as we cut off of our line, we may end up with up to 30% error in our desired objective. And this whole thing is the work that we put in enable this to be done sort of instantly. This is a constrained optimization problem that optimizers such as MATLAB or Python have tools to just go ahead and instantly solve this. Now that's the first pass design, where we say, here's an objective that we want, give us the design. Now, this requires us to know what we want. What if we have a design that we built and we don't necessarily know how to frame what we don't know about it? And so this is another case study. Now this is not this doesn't use the oscillator design. This is still a printable design. It's using paper folding in terms of a structure. But in this case, we had a blimp, and we're trying to move this around, and it needs to perch on a handle. And so we grabbed onto it, and as this blimp moved around under high air current, the gripper itself failed, and the blimp did not remain perched. This is another framing of the design problem. We have a structure. Now we need to evaluate its failure modes and iterate to come up with the next design. And so we can go through, use our tools, again, use the same kind of pipeline through the constituent equations, the physics-based modeling and simulation, reduced order modeling to give us an optimization procedure to go ahead and identify the source of failure. That this fell off because the strength of these two segments were too weak. There are other geometric constraints on this, performance constraints, geometric constraints. We can feed that all into our optimizer and come up with a solution. In this case, it's a reinforced structure with ribs, with folded ribs. And that gives us the ability to build a structure that can maintain grip on the perch despite the high current air currents around it. And of course, if we didn't do this optimization, if we just went ahead and tried to make it as stiff as possible, it would end up being a lot heavier than it may need to be. And we're talking about a blimp. Weight is critical to its performance in other parts of the system. So we can take this framework, these two examples, and abstract it to our general approach to solving problems on the side of computational design. And here are a bunch of other problems, and I won't necessarily go through the specific details. If you find something you like, feel free to ask questions and we can go into more detail. But ultimately, we start from some objective, some robotics design or manufacturing goal that we'd like, and we figure out what is the core resource that is inhibiting access to that solution. It could be a question of money. It could be a question of knowledge. It could be some other resource metrics that may be some of these more canonical robotics parameters. We figure out how to model the objective, the requirements around that resource. We use our ability to model systems both through data-driven techniques and computational techniques to go ahead and create an optimization problem. Here's a few other problems here. With that optimization problem, we can now wrap this into a computational implementation. This computational tool, we can then go ahead and solve in a way to generate a solution to our problem in a general fashion. And that gives us the ability to improve access to all of these technologies and ultimately improve access to creation. And so with that, I'd like to wrap up here and say, I talked a lot about computational design and manufacturing. Ultimately, that core principle of low order modeling implemented into computational tools gives the ability to create at a much more accessible level. What I want to see come out of my research, and in fact, what come out of sort of the entire space of research, is that more people take part in the engineering creation, in the story of technology from the very beginning. Not just having more people use robots, not just have more people have robots, but have more people create robots as well. And so with that, I think this is the time to widen the conversation beyond just me and incorporate all of you as well. I'd like to hear from you. I'd like to hear from you. What did you take away from this? What struck your fancy? How are you going to go through and now apply our privilege as engineers, as technologists, with access to a lot of resources, to give those who have access to fewer resources in terms of money, in terms of infrastructure, in terms of knowledge and experience, a seat at our table. With that, I'll open it up to all of you guys.
Any questions from the floor, or can I use speaker introducer privilege to throw one out? So the fundamental question I want to ask is, how can programming really accelerate this process of democratizing access? Right. So at some level, we like to think of programming as, oh, you just need a laptop. How expensive are those? You can get access and start doing things. Where can code really make this killer advantage to democratizing access to the hardware you need when you embed intelligence into a body?
Great, thanks, Jeff. I think that's a very interesting question, which I will reformulate a little bit, because that would be the thing I would want to talk about next anyway. And it's this idea of where code and where sort of computation fits into the entire pipeline of creation to begin with. Now, computational design and computational fabrication is turning, code is using code and using computation as a way of expanding the role of computation within creation. It's giving the ability to generate hardware using software constructs. Fundamentally, though, what I view computation and code as is a way of capturing design intent. And it's a way of taking a bunch of humans with a bunch of different backgrounds, a bunch of different experiences, and a bunch of different ideas, and unifying it around a single language. And I think that's a very powerful thing, because not only does it let people know what, or it lets people express what they want to express, but it lets people know what other people are expressing. It lets people share information, ideas, and sort of grow the space of the conversation, provided everyone can speak that same language. And this is sort of a question that is not limited to just here, but it goes around a lot. Is, this is how does code either facilitate or inhibit that exchange of ideas and that ability to express in sort of this in this broader space? If there's a high barrier to access learning the code, then coding may provide an inhibition. If there's a high barrier to access to exploring, to executing that code, again, you have a high barrier. If we can instead use code to say, it's very easy to learn how to express in this language, it's very easy to explore in this language and learn if what you're expressing is what you intend, and learn and see what other people are expressing and see what they intend, then all of a sudden it becomes a powerful tool to be able to democratize conversation, democratize access to this conversation. And I think that's where we need to go. Thinking about what resources are necessary to start participating in the code portion of design, to know what resources are necessary to execute and to exchange and so on. And so that's where this goes. The more we can make use of code in a way that more people can speak in that code, I think that provides a very convenient and effective channel to build on the idea of creation.
I think with that, we are out of time. So let's thank our speaker again.
Great, thank you all. If I do encourage more conversation. If there's other things that you found that you want to talk more about, reach out to me, send me an email, and let's keep this conversation going.